Hello again. This is the second lecture of our course. In the last lecture, we primarily spent our time on review of classical continuous time or analog control systems. Chapter 2 of the book by Franklin and others. I strongly recommend to you that by now you should really review as much of that chapter as you need, and some of the homeworks assigned will be based on that chapter. Today we're going to go full-fledged into digital control systems, talk about its analysis, its stability, how to design it as an introduction to the entire semester. Here we go. So this is introduction to discrete or digital control system. Digital controls are much more efficient and cost-effective because of their fate is attached to the computing technology and the VLSI design of chips and single-board computers and so forth. They are very much used in industrial robots as well as other kinds of robots that you could find in our laboratory. Hopefully some of you will be doing a project on robots in the lab. It also can be used for optimizing fuel economy of automobiles or other operation of other appliances and machines like washing machine and dryers, etc. Even a rice cooker, for example, uses digital control. And also decision-making ability and flexibility in many control programs will be a major advantage. So, due to, again, availability of low-cost digital computers and advantage found in working with digital signal, we are promoting this particular subfield of the control system. The types of signals which we are concerned about in this course are quantized signal. The quantization is the process of representing an analog variable by a set of distinct values of that variable. A discrete time signal is a signal defined only at discrete instance of time. So you can see, for example, at this instant, this is the definition, all the way to the next sample, and so forth and so on, all of it. This is a sample and hold version of this analog curve. A digital signal is a discrete time signal with quantized amplitude and can be represented by a sequence of numbers. And here they are. These are the digital signal, and these values are going to be represented by a digital word, a certain number of bits in the memory of your computer. So in using digital controllers, it's required quantization of signal both in amplitude and in time, such as this, for example. So, for example, here is the idea of quantization and sampling. You have here Stafford Graf, a famous tennis player from Germany. Her image has 24 bits per pixel. A coarse sampling have only 1 per 4 pixels, have one of them with 1 bit per 4 pixels, and then even course of quantization, you can see the difference in the image. It's very, very difficult. Both of those are going to be two different coarser sampling and coarser quantization. So these two values, these two effects need to be important in realizing digital control system. Again, we are dealing in this course with linear system. What is linear system? Is one which in which principle of superposition applies. You recall maybe in your signals and system courses, if you have a system is linear, you have, let's say, input u into that system and it gives you output y. If you have a times u going in, output would be a times y. Or if you have y1 as one, u1 as one input and u2 as another input, respectively getting y1 and y2, then a times u1 plus b times u2 applied to the system produces an output which is a times y1 plus b times y2. That's the superposition. If that doesn't hold, then the system is nonlinear. And normally these linear systems are described by linear differential or difference equation. We'll go into difference equation soon. And as you saw in the review of the first lecture, you can convert a linear differential equation or a linear difference equation into a state equation, which we need to have for modern control applications. Now, if the system is time invariant on top of being linear, if all the coefficients are going to be constant and they don't vary with time. If even one of them changes with time, then the system is with time varying. So discrete control system are systems where one or more variables can change only at discrete instances of time. They are not continuous. You are missing information in between intervals. The interval between two discrete instances is taken to be sufficiently short. If it's very, very, very short, then it almost approximates a continuous system. Continuous control system signals are continuous and described by differential equation. Here, described by difference equation. The sampling process of a continuous signal basically replaces the original continuous time signal by a sequence of values at discrete time points. Sampling process is again followed by quantization. And it's a process that the signal sample value is being held until the next signal comes in, the next interrupt comes in, or the next clock tick is coming in. It's important to note that sometimes sampling operation is entirely fictitious and has been introduced to simplify the analysis of control system. I'll indicate that to you in due course. Many digital control systems are based on continuous design techniques. Now, if we have a good knowledge of that in design, as we said last time, through emulation, you can convert that analog controller in S-plane into a frequency for the discrete system, which, as you will see soon, we call it the Z-plane and Z domain. So here's another architecture or block diagram of a digital control system. You have the input, you have the output, you have your plant. The plant has some disturbance, could have disturbance or noise, and you could put that noise into the feed-forward controller and send that into an actuator like a motor, and then this feed-forward control would reject the disturbance or noise. We briefly mentioned that idea. In the digital controller shown in this dotted box, you have the digital computer or microprocessor, you have analog to digital converter and sample and hold unit, the one which sends a discrete signal into a staircase signal. You saw that last time. And then, of course, clock handles the organization of and coordination of all of these blocks. And then the digital computer acts on the digital information coming from here, which is the error between the output, the transducer or sensor changes the output from voltage to from a physical quantity to a voltage. It could pick up some noise because of sensors, and then it goes to a filter. You could filter the noise, and then that output is compared to the input. You pick up an error here. And so the error is going to be a signal which influences your controller inside the digital computer. Coming out of the digital computer is actually your control signal in digital words. And then those will go to digital to analog converter. You finally get to hold it, and that hold gives you an analog signal for the actuator to run the plant. So this is a more complete block diagram than the one I showed you last time, and these sets of slides, which are not based necessarily on neither of those two textbooks, are already on Dropbox. So another way of looking at is what happens to the signals in digital. You have analog signal coming in, it converts into a bunch of words, digital words. The digital computer acts on it. Maybe a PID controller is sitting there, an algorithm is sitting there to realize that the PID controller. It gives you a bunch of words as a control signal, and that converts into an analog signal which has to be held in order for the actuator to always have a voltage available to it. So it's going to be held like this. And then finally the actuator produces a signal which is continuous, and that goes to the plant, gives you an output to be compared to the input. Again, you have an error here. So what are the specific tasks and objectives of these different blocks? Sample and hold is a circuit that receives the analog input signal and holds this signal at a constant value for a specific period of time, mostly one sampling period. A to D converter, analog to digital converter, is a device which converts analog signal to digital signal, usually a numerically coded signal. And this converter is needed as an interface between an analog component and digital component. So you can think of A to D and D to A, both of them as interfaces from analog to digital and back from digital to analog. A sample and hold S/H is often an integral part of a commercially available AD converter. So because that's such a necessary component, they manufacture it together. The approximation process by limited number of bits is called quantization. Okay. And we saw that before. And D to A converter is a device which converts digital signal into analog signal. And it's needed to interface again between digital component and analog component. The plant or process can be any physical object. Could be a robot, could be a rocket, could be your automobile. You could be, for example, a subsystem of your automobile, like cruise control or fuel mix control and so forth. The most difficult part of the design may lie in the accurate modeling of physical plant. That's always the case. Your control, which is based on model of the system, is just as good as that model is. If the model has inaccuracies, unmodeled dynamics, it has variations that are not recognized, or you have made too many assumptions, then that control could be suspect because of the model is not quite represent the real system. In designing digital controller, therefore, it's necessary to recognize that mathematical model of plant in many cases is only an approximation of the physical one. This is essentially what I just told you. The sensors or transducer again, a device that converts an input signal into an output signal of another form. For example, converting a pressure signal into a voltage. The output of transducer is always the voltage, but the input may not necessarily be. Types of sampling, you have periodic sampling, which is most common one, multiple order sampling, which is not really as common, or multi-rate sampling. You may have different rates for the system. In this course, again, because being an introductory course, we are only looking at the constant rate. And you could have random sampling. That is even more really complex in terms of the sampling process. So you go from a simple one all the way to a most difficult one. Those are all available in real world. So what is quantization and what's quantization error? Quantizing the process is the process of representing a continuous signal by a finite number of discrete values. The quantization level Q is defined as the range between two adjacent decision points. Okay, it's full scale range divided by 2 to the power of n. N is the total number of samples you have. So this is basically divides that into a value called quantization level Q. What's the quantization error? Analog digital conversion results in a finite resolution and varies between 0 and plus or minus 1/2 of this Q value. So it's the quantizer, you have input and output, and it could be, quantization error could be at most half of this sample, here or here, okay, shown by these dotted lines. So this is the first quantization value Q, quantization level, this is the second one. So here you have a continuous signal x of t, and then you sample it at so many different samples. You have from here to here, and then the hold is holding it, and what you see here is essentially another signal y of t. The difference between those two is going to be a quantization error, which should be between 0 and 1/2 of the Q. You just saw that. So it's somewhere in between these samples. And as you can see, you are missing a lot of these values. You miss, then you come to this value, up to there, you miss this whole value, and you replace it by just one single value. So you are errors in every step of the way. You have error. For a small quantization level Q, the nature of the quantization error is similar to that of random noise, which is shown here. So that is the square of random standard deviation is equal to Q squared divided by 2. Now, for data acquisition, conversion, and distribution system, is in this situation operation involved in the signal conversion, multiplexing and demultiplexing, basically having multiple signal being sampled simultaneously together, and then separating them out through demultiplexing later on. Of course, sample and hold, you saw that. A to D, okay, and D to A. So this is quantization and coding. D to A conversion is decoding. And here you have physical variable going to transducer, to amplifier, low pass filter, possibly get rid of the noise, analog multiplexer, sample and hold, A to D goes back to digital controller. And there it goes to a register, to demultiplexer, digital to analog, and to the hold and so forth. Later on, when you go to the lab and start working on the project, you need to ask your mentors, our PhD students, to give you a sort of a tutorial of what kind of digital controller is on that robot or on that particular car. We have a driverless car in the lab which you can join and work with one or maybe two PhD students. So this is analog multiplexer, a device that performs the function of time sharing, an A to D converter among many analog channels. So you have many analog channels, but they only can serve one of them at a time, and then they multiplex it, and then they get second and third and fourth and so forth. And there is a process called sequencer, which sequences them together. The demultiplexer is a device which separates the composite output digital data from the digital controller into original channels. And this is the architecture for it. And sample and hold circuits, actually this is for sample and hold circuit. The sampler converts an analog signal coming in here into a terrain of amplitude modulated pulses here, and the hold circuit holds the value of the sample plus a pulse signal over a specific period of time. So these things are for you, your general knowledge. In the lab, you just have a chip, you can identify it on the control board. So there are, on sample and hold, there are two modes of operation: the tracking mode and the hold mode. For example, you track it here and then you hold it, or you track and you hold it, track and hold it. So tracking mode is when switch is closed, the charge on the capacitor in the circuit tracks the input voltage. Talking about basically here, it's being held when the circuit is closed. And hold is when the switch is open. The operating mode is the hold mode, and the capacitor voltage holds constant for a specific time period. These are types of A to D converters: successive approximation type, integrating type, counter type, parallel type. And this is the first one, okay? And you basically send signals one at a time, 1, 2, 3, and so forth, all the way to the end. They take turn and they send the signal through. And then, of course, your control logic knows which signal is what and uses them accordingly. So in analog to digital converter, you basically have three kinds of error. Offset error is that if this is the actual analog signal, the values, if you put a curve fitting on the discrete values, you get something like this. And the difference with that is called offset signal. And this is what's called linearity error. If this is your analog signal and this is your curve fit of that as a linear function, then it's called linearity error. And then the gain error is the one that actually the difference between any location between these two values, the analog and digital, would call gain error. So in DAC converters, you use weighted registers, and you are what's called R2R, R2R ladder circuit. Again, these are just for your, here it is, R2R ladder network, R2R, 4R, 8R, and so forth. So that every time you have a different signal going out into D to analog converter as an output of it. Now, if you want to reconstruct the input signal by Holt circuit, the purpose of the Holt operation is to fill the space between sampling period and this roughly reconstruct the original analog signal. So here is actual analog signal. These are the sampled values. You see all the sampled values. These are the held values. And so this signal, again, like a staircase or a stair coming down, is your output of your Holt circuit. And you could have, let's say, in here, you see a zeroth order approximation, because this signal become constant is like t to the power of 0. T to the power of 0 is 1, or 1 times whatever this value is. These are all zeroth order approximation. That's why it's called zero order Holt. Now this is first order Holt, where between the samples you have a linear function, like instead of 1 you have just some value of time t, and that's going to be the difference between two samples would be a line coming in. As you can see, the error in here is somewhat smaller than the error in the sample and Holt, but this is much more difficult to realize it in a digital control system. And because of the advent of computers and speed, it is not really worth doing that. Holding signal is good enough. Or you could even have polygonal Holt. Between the two samples you have a polynomial. Between this sample and sample you have this polynomial. Rather this one, and so forth. So this analog signal is represented by this digital signal. Again, those are good for theoretical studies and publishing papers, etc. But sample and Holt, that is best good enough. So digital controllers operate only on numbers. They are extremely versatile. They're performed by simply using a new program. Digital components are rugged in construction, highly reliable, and often compact and lightweight. And controlling of processes is possible to take into account all process variables and thereby to accomplish optimal control of industrial processes. They have schemes for being flexible. You can program and reprogram digital controllers. So we will now switch to another set of slides. This one is again coming from a book by NICE, Control System Engineering, and in the digital control system. You can see here two systems. Both of them are trying to control azimuth position of a satellite dish or satellite antenna. Okay, and this is the analog where that you can do that. Basically, you measure it through a potentiometer. You know the angular position of the sat antenna. So part A is analog control. Digital control, you take that information from the position, you put it into a transducer and send the position A to D and D to A, and use a computer to analyze a controller. So you will have digital devices, interface devices attached to it, and analog controller can be changed into a digital form that you will learn to do later on yourself. So you, in digital control system, you are asked to place a digital computer within a loop. So here's your loop. Normally you have analog control here. Now you put a digital computer here. Digital computer is like oil and this is like water. They don't mix together. You need to have some kind of interface to be able to work together and exist simultaneously together. So A to D and D to A come before and after the digital computer, and the plant will be happy. It has the right kind of control signal going in there. So again, analog to digital converter, this is one possible mechanism that you have. You have a bunch of switches, which switches from most significant bit to the least significant bit. For example, 2 to the 0, 2 to the 1, 2 to the 2. There are 3 bits over here. They are combined together to give you an analog signal. So what are the steps in analog to digital conversion? You have an analog signal here. You have an analog signal after sample and hold. Here you have. And these values are digital numbers, 000, 001, 010, 011, and so forth, all the way to 111. That gives you basically 8 different values. This is 0th sample, this is the 7th sample. There are 8 of them, 2 to the power of 3. Conversion of sample to digital numbers is like here. So at this time, all of these are going to go into the memory of your digital computer, and then they can be used for operational in your control loop. Now there are 2 views of what's called uniform rate sampling. You have switch opening and closing, switch opening and closing here. When switch opens, you have a piece of the analog signal. When it closes, you have nothing. Again, a pulse. So you have a bunch of pulses with the width of TW, in this case T. This is 1 pulse, 2 pulse, 3 pulse, and so forth. So here you have product of time, waveform, and waveform sampling. Again, that is another way of representing that output. You have a terrain of pulses being multiplied by your function, you will get that. It's essentially is a convolution process that you have seen in the digital signals and systems courses. You should recall convolutional integral. In this course, we will show you convolutional sum. Okay. Now, this is how you can model a sampling with a uniform rectangular pulse. And we will show you later on that basically here you have a terrain of pulses that you saw in the previous slide. Each of them pulses have different kind of amplitudes, depends on the input function obtained at that particular sample. We call that F star. And then in this time, in the rectangular time with rectangular option, that will come TW multiplied, T sub W multiplied by that. Now, if you, later on, we'll show you the Laplace transform of this function. Laplace transform of this function is going to be e to the minus kt times the Laplace transform of a pulse, which is equal to 1, as you know, is the first entry in the Laplace transform table. So here you have ideal sample and hold. sample here and hold it there. So here is the sampler, and the hold will change it to this. Okay, so that's very simple and I think straightforward. And again, here is analog signals, a unit step, ramp, t to the power of n, e to the minus at, and so forth and so on, sine and cosine. Laplace transform of this is 1 over s squared, n factorial over s to the n plus 1, e to the minus at is 1 over s plus 2. Now, we have not yet defined Z transform. We will do that briefly here, but in the future lectures, we have a full treatment of Z transform. But for the time being, Z transform of a step is Z over Z minus 1. Of T is the sampling period, T times Z divided by Z minus 1 squared. But corresponding to ut, you have u of kt. Corresponding to tt, you just have kt. Corresponding to t to the power of n, you have kt to the power of n. As you can see, you now have a whole bunch of new signals, all discrete signals versus analog signal. Okay. Therefore, the objective of Laplace transform and Z transform are very similar in the following sense. You have a differential equation in this domain. Laplace transform changes them to algebraic equation that you can easily manipulate and use. In Z transform, takes the discrete signal, converts them into algebraic form where you can manipulate and check stability and so forth and so on. Some properties of the Z transform of AT is A times transform of F, called linearity theorem. Z transform of F1 plus F2 is F1Z, F2Z. Z transform of e to the minus AT, F of t, is F of e to the AT times Z as an argument for this function, complex differentiation. Z transform of F of t minus nt is Z to the minus nt F of Z, real translation. Okay, or we will later on also put them in the form of a delay. Z transform of a t times analog function F of t is minus t z d f z d z, complex differentiation. F of z, the initial value of a function in discrete is z going to infinity of f of z, initial value theorem. Final value theorem in discrete form, f of infinity, like the steady state error, is limit of z goes to 1, 1 minus z to the minus 1 times f of z. Okay. So these will come handy later on, and we will review them and work on them time and time again. So, sample data system. We said previously in last lecture, a sample data system is a system where analog and digital components coexist together. So this is a continuous signal. This is what you have been doing all the time in your first control class. Sample input is here, you sample the input, then you have R of S become R star of S, then goes into the plant. You could have sampled output like here, or you could have sampled output and input together. So there are several places you can sample signals together. And later on we will show you actually how to reduce this block diagram in Z transform. You have maybe sample in the feedback, sample in the feed forward, input, output. We will give you the potential values of that in Z domain. For example, you have R star here, it stands for R of Z. Then G becomes G of Z, and then the output will C of Z. So this process, whole thing is represented by a block in Z domain, input R of Z, output C of Z. When you have a cascade of two analog signals, then you represent it by G2 times G1 first in S domain, and then convert it to Z domain. So this is not, this is just G2 G1 of Z, and of course the output. If you have a sampler in between the two, then this becomes independent of the other one, and you have G1Z, G2Z, G2Z, G1Z. Goes from the second one backward to the first one. G2Z, G1Z, again, input, output, R and C. And then here you have basically signal G1 is part of, multiplied by R of S, that it becomes like your reference input. So you have R times G1Z, then G2Z and CZ. Those are all different way of representing that. And later on, you will be asked to work on this kind of thing as homework, and of course, questions maybe on your midterms. So steps in block diagram reduction in Z domain. We get more of that later on, and of course MATLAB can also reduce the block diagrams for you. Here is the sampler in the feed forward of this. This is a sampler in output, input, feed forward, and it's a feedback loop. So you can actually move G1 into the output and have a G2 times H. So you compensate here in the loop for the absence of this block. So you get a simple line here with magnitude 1 and a sampler in feedback with G2H of Z, H of S here in the feedback. And then you, because these two samplers, you could replace that simply by G times H of Z. And then this will be simply G1Z. So now you close this loop by using basically 1 divided by 1 plus GHC, which is this, and cascaded with that. Then you combine these two together. Now you got a reduced block for that kind of system, for that whole system. Okay. And no, we will go further, more and more onto these things in several practices. And digital system for a skill assessment, you have here G1 and G2. We want to find the G of Z. You can look at that as an exercise for yourself. Computer-controlled torches cut thick sheets of metal used in construction. So here you have different cutters are controlled by digital controller, and the sheet goes through it, and it comes out into a small strips of let's say metal, like that. Now I mentioned to you that we have two planes. We have S plane for continuous system, Z plane for discrete system. The imaginary axis here, you noted last time in our presentation that anytime you have a pole on the j omega axis, you're going to have purely oscillatory situation. If you have poles in the left half plane, it will become stable. If you have in the right half plane, it becomes unstable. Now, what you see that there is a mapping between S and Z plane. Z is equal to e to the S times t. That is definition of Z parameter. Z is equal to exponential of S times T. S is the Laplace transform and T is the sampler. Therefore, through this mapping from S domain to Z domain, the left half plane goes inside the unit circle. This is a unit circle. The J omega axis is the actual circle itself in its circumference. And the right half plane is going to be outside of, anything outside of this unit circle. It can go anywhere. So in discrete control system, digital control system, if your poles end up inside the unit circle, you're in good shape. It's going to be a stable system. If it goes on the unit circle, it's oscillatory. Now there is, if it's outside of the unit circle, it's going to be unstable, which corresponds to the right half plane. There is another catch to this. On the J omega axis, if you have repeated pole, it's still unstable. Same thing here, if you have repeated poles on the unit circle itself, the system is still unstable because you have a parameter K is multiplied by your output response and K is going to infinity. Here, T is multiplied by the response. So T or K, as K or T goes to infinity, is just as bad. It makes system go to instability. So always remember unit circle. When later on you see there are root locus, we put this on top of root locus and see where the roots go. Roots go out of the unit circle. It's equivalent to you going to the right half plane, like that. So let's look at the missile control system. Has an airframe dynamic. Find stability of a missile control system. A is the missile, B is the conceptual block diagram. You have airframe, you have sensors somewhere here, A to D, computer, fed by analog to digital converter because of the tracking data, and then you have digital to analog converter, amplifier, and possibly actuator, and then they will start. The input to the system here is a trajectory, optimal trajectory of the rocket or of the missile. Then here is a block diagram of that missile control system, and then you put it into this is in the S domain. You have a gain here, and this sample and hold. I mentioned to you that it's 1 minus e to the minus t times s over s, and this will be derived for you later on. For the time being, just take it for its face value. So C is the block diagram, D is the block diagram with equivalent signal sampler. Okay, so this is now a complete digital control system. So again, you can look at this and ask yourself how you could basically represent this in a Z-S domain. Later on, you can do that. Now, you remember from analog system and your control class on route stability table. In route stability, you put the highest order of your polynomial, and you go to all the way to the lowest one, which is 0, and then look at the first column. If you have any sign changes, system is unstable. In this case, you see that you have 1 and minus 19, 1 sign change, and that's system is unstable. Okay, so again, exercise for you. and how to go from a digital control system with a sample and hold here, analog signal with one sampler, or this kind of control. You saw that before. You could take it all the way to here, and you could reduce it into a Z-transform equivalent system. Now, you may recall that in analog system, we mentioned to you last time that an array going from the origin in the left half plane makes an angle theta with the negative real axis. Cosine of theta is the damping ratio. We have the same thing in discrete, in the Z plane. Look at what I show you here. These lines, these curvatures correspond to zeta is equal to 0.9. This one corresponds to 0.7, corresponds to 0.3, 0.2, 0.1, and so forth and so on. These lines are starting from 1.1 and 10 here, and these are going to have be lines that you will see later on that you could use it, in fact, as a part of your cheat sheet coming to the exam. You can have these sheets with you. We'll show you how to do that. And then here you have constant settling time with these co-centered circles. Okay, and then these are constant peak times of the signal. These may not be obvious right now, but we will show you later on how it works. Now, in fact, this is partial, getting into the partial explanation of that. Here's what I was mentioning to you. You have an array going from origin in the left half plane. It creates an angle here. The cosine of that angle is equal to damping ratio. Or cosine inverse of damping ratio is that angle. Sine inverse is this angle. Okay? And then, as I mentioned to you, this distance is omega n, natural frequency. Okay? So if you want many different damping ratio, you go zeta is 0, zeta is 0.2, 0.5, 0.7, 0.8, 0.9, and zeta equal to 1 here. So that is how you look at that. Now, what is going on is that these kind of parameters and these kind of regions, which are desirable regions for analog design, we convert it to desired region in Z plane, in the other plane. This is a generic digital feedback control system. You have G of Z and H of Z. And you have R of Z and C of Z. After you have basically represented so you could have, for example, in this system, you could have a 0 at -1, a pole at +1, and a pole at +0.5. Okay? And you can find the closed loop pole, the closed loop transfer function of it, and you can also do both root locus. Remember here, we mentioned that you have a 0 at -1, a pole at +1, which is here, a pole at +1, which is here, and a pole at 0.5. So one pole at 1, one pole at 0.5. Both these are all, that's your unit circle. The black circle is your unit circle. The blue is your root locus. Now remember that we said to the left of the odd number you have a piece of the root locus. This is number 1 to the left of 1. Here is 2, you don't have any. Here you have 1, 2, 3 elements, or 0 and pole combination. To the left of that, you have also root locus. So first thing you want to do is to identify the pieces of the negative x-axis, which are, or in fact, the whole axis, which is part of the root locus. Between two poles, you need to have a breakout point. The branches have to break out and go somewhere else. You have one going here, and then one comes here and goes to the zero, a finite zero. The other one goes to an infinite zero somewhere here. These are the two branches of the root locus for that system you saw here, right here. Now, notice what's happening. As the gain increases on this digital controller, the poles start moving. The closed loop pole moves here, moves here, moves here. Then it becomes oscillatory and becomes unstable. So the system is only good inside here, not including the point on the unit circle up to here. This is the only segment where the system can operate in a stable mode. So if you blow up that piece of segment I showed you, that's the pole at 1, the pole at 0.5, and you have a zero somewhere here at -1, which is about this much here. And the branch of root locus is moving here, and then it hits a locus of 0.7 damping ratio. 0.7 damping ratio is roughly for about 5% overshoot. So at this point, this will become a nice operating point for you on the Z-plane, which is going to be 16.6 degree difference between this value, between the real axis, and the values at here are going to be the operating point of your control system. So you have a root locus for the system with constant 0.7 damping ratio curve, which is this. And then of course you can do a step response of this. You will do pretty much all your homework. Most of your homework is going to be done by MATLAB, and you're going to be learning about how to run the control system toolbox. Here you could do a step response. Now if the sample is too rough and too slow, then this becomes sort of like a bunch of small ladders, laddering, stepping going up, stepping, leveling off here. So it all depends what sampling period has. And for value of k equal to 0.0625. 0.0625 corresponds to the value of k right at that point, right there. Okay. Or right at that point, somewhere here. Okay. So if you have a lead, let's say lead compensator, an analog signal, a pair of poles and zeros here, the plant here, you can, through emulation, you can change that to G of Z, and then run it on the Z transform version of the plant. So both plant and the controller or compensator will go into the Z domain, will be converted in Z domain, and then you have an ultimate transformed digital control system block diagram. Okay. And the closed loop response for the compensated system, showing effect of 3 different sampling. So you have sampling value of 0.01, which is very small. You cannot hardly see it on that blue curve. Sampling of 0.026, which is more than twice this. You have this value, and then additional one would be here, which you cannot see it very good through the audio on the presentation, but it goes up to here and comes down. As you can see, overshoot goes up as the sampling goes up, because the analog signal, the plant is waiting for signals, and the whole signal is holding it too long. This block diagram shows computer emulation of a digital. So essentially, you have controller in S domain is now emulated into a Z domain controller. This controller used to be a PID in S domain, but now it's equivalent of a PID in Z domain. Okay. Now the accuracy of this process depends on the sampling period. If the sampling period is very, very small, it's a good approximation. And so again, that compensator that you saw, you could represent it by a block diagram like this. We will show that later on. This is going to be Z to the -1, Z to the -1 here. We will show that later on to you. Flowchart for GCZ for this particular is shown here. This is the block representation of this controller. Okay, you have Z plus 0.5 here, then you have Z squared minus 0.25, Z plus 0.7, realized in this way because this is Z minus 1, Z minus 1. You reduce these blocks, you come up with these things. Remember the antenna control system at the beginning of this set of slides? Here is your motor and load. These are the gears, power amplifier, preamplifier, and potentiometer. That's the analog signal. Digital would be sample and hold here, and computer and digital to analog converter. Analog to digital is in the feedback loop. You also have a digital reference input after going through A to D, and then you have a power amplifier, motor and a speed in S domain, and the gears, a 10% gear. So this is a digital implementation of that control signal. So putting some numbers into that digital control system or simplifying it, you get this kind of system for the antenna azimuth position control system. And again, if you look at the here, you have a pole at 1, a pole at 0.843, and you have a 0 at minus 0.945. So you have a pole at 1, a pole at 0.8 something here, and a 0 at 0.95. And again, your root locus shoots up, and after about sometime later, it leaves outside of the unit circle. As long as the branches of the root locus are inside the unit circle, the system is stable and you're okay. You'll be in good shape. Again, a step response. Here is another a simplified block for a plant which has only 2 poles and a lead compensator. Here's the step response for that system. So this is how you implement a digital controller for flowchart of a lead compensator. We will show you in detail later on to go from S domain of a lead compensator to the Z domain. Once you go to the equation in Z domain, like a set of zeros and poles corresponding to emulated values of zeros and poles of the in Laplace transform S domain, you can always we'll show you how to draw the block diagram for to represent your compensator. And in this case, you have a whole circuit, and in this case, you have both plant and perhaps some transducer, which are dynamic, or some additional dynamic, and you have two samples here, a whole circuit holding this quantity, and then another one holding for that one. So you may have two different plants that you could represent them in this fashion. And again, later on, I believe in chapter 4 or chapter 5 of a book by Franklin, we will come to these kind of block diagrams, where you have a sampler in feedback or feedback or feed-forward loop, and the question is, what is C divided by R in S domain? Or what is C star or R star? In this case, this is a C star right there. C star divided by R star, which is this. What's that transfer function? That's the kind of question that will be represented, and we will tackle them later on. Here is another configuration for a control system with some specific values, and you can represent them by this, and here again additional plants in S domain, then going to the Z domain, and so forth. And it's very common that you have integer numbers for poles and zeros in analog, but in digital it becomes not necessarily whole numbers. It could be a decimal number for location of poles or zeros in Z domain. So this is a swinging motion, let's say like a pendulum. That could be a block diagram for that. This is a floppy disk drive that you take it for granted when you use your computer. Here again is the Z, S and Z table. You will need copies of some elements, rows of this, when you take exam, and we show you later on. Again, Z transform theorems, we went through those before, and we went through this before, and that's it. So, in summary, in these two lectures, we have reviewed the classical control methodologies and analysis, some part of design for you, and we also introduced a state space formulation, and in this lecture we gave you a complete, more or less a complete introduction into a digital control system. And when I come back, see you next time in person, please bring all your questions. We go over them, and we also introduce you to the projects in the lab. Thank you very much.